Let's see. Ooh, I'm up to 20%. Okay, so technically we've only got two chapters left. Kind of in my mind, both these chapters should be joined, but there's not much you can say or do about that. Some books have them joined together, and some don't. I can see the reason for doing both. So center of gravity is kind of revolves around the concept of if you had an object and you wanted to balance it, you're going to have your finger in the place that's directly below the center of gravity. So if you had the center of gravity was right here, and you put your finger over here, you're going to get a moment, and this object's going to fall off your finger. So if you want to balance something, you put your finger, here's your finger, directly under it to support it. So you can find center of gravity experimentally really easy. That's not an issue. But the issue is if it's connected together with all sorts of things, you need some sort of equation to find it. Now, let me kind of put it to you like this. I don't like the way he takes off and covers this. The first thing he starts talking about is one-dimensional objects, which, I mean, I get it, but it's kind of silly, but, we're just going to go with it. So it's kind of like saying a pencil, Okay, so I get it. You hold it, you find the center of gravity. The only place you can move about here to find it is on the X. So what you're doing is you're summing, that's true. You're summing that, but you're trying to find the moments where the moments are zero about it. So it's better suited to go to a two-dimensional object. So if you think about it, you can find a particular location, which he calls X bar and Y bar, in which you can put your finger directly below it. If you put your finger directly below it, there's no moment produced there. So moments are the key. If, however, you went over to the side and put your finger over here, the thing would fall off. So there would be an inherent moment. So what you really need to do is you need to pick a coordinate system. That's the first thing, which is what he does. And he says, okay, let's integrate all of the moments. So he takes a little d weight, which he's showing this as a little bitty cube looking thing. And he says, hey, I want to integrate all of these from this value times the little d weight across all of them and find the actual g would be the actual location of this. So what he's saying is this. Okay, hang on. He's saying, okay, I want to find this value x bar, which is the location of the centroid, the x location where I put my finger underneath it. This is the weight of the whole object. So let's say this thing was 1 pound. And I'm trying to find the location in feet, inches, whatever. So what I do is I integrate this across all the dW's. And multiplying this out, this would be the moment that would be produced by a weight located at one location, at one point, times the x bar. And that would be the rotation or the moment about this axis right here. And he says, okay, that's got to be equivalent to the sum of all the little d weights put together. So since you know the weight, this value is the w, you divide it underneath, and that's your x bar. Now, the key is the d weight or d volume or anything else. So what happens to you next is he goes on and he says, okay, I might have 3 dimensions. Okay. Well, there's 3 of these that look exactly the same, except they have the individual coordinates there. Nothing new. Then he says, this is what's funny. He says, okay, well, let me confuse you by saying I'm going to move to mass now. And he's doing this again with dm. Now, weight is equal to mg. So I guess technically you could do this and G, and you'd have the equations that were above you there. Okay, so there's really not anything different there. Then he says, okay, a centroid of a volume. Okay, so he's confusing us even more now. So when you say d volume, how is that related to d mass? Okay, well, density is equal mass per unit volume. So if I just did this times rho times g, guess what? It would be the same thing that I would have before. Now, it could be that part of this is, like, say part of this object is steel over here, and part of it is wood. And in that, the density would change. This would be a different density than this, but, you know, he never goes there. So what I'm saying is this is technically the same as this, which is technically, well, I guess you could say, oh, I'm sorry, here it is, which is technically the same as that. So I don't know if that makes sense, but then he goes off and he talks about an area. Now, believe it or not, this is more often what we're looking at, but how does the area relate it to the weight? Well, if you took a plate, a steel plate, for example, and that plate was, say, 1 inch thick throughout, what you could figure out is the weight per unit area here. And then you can basically multiply that, the weight per unit area, on all these. And again, you're back at the original. So, but it turns out, more often than not, we deal with this thing this way. And the reason being is because D area can be broken down pretty easy. Here's what I mean. When you were in Cal 1, 2, 3, you had some function, right? And he was mostly interested, when he's integrating and looking at D area. So this relates back to Cal 1, 2, and 3. So that's why this is kind of more of the target. You can multiply the area times anything, and you can work your way back to the mass. Okay, then he gets to the centroid of a line, and to me, that's okay. It's just really kind of, yeah. And he goes through this. I kind of discount this as follies. So let's go in and do a problem, say. Let's do, let's take a look at this one, if it'll come into focus. Okay. All right. So what he's going to look at is he's going to say, I want you to find a centroid of a plate. That plate's going to be a certain height and a certain base. So usually H is looked at as the height and B is looked at the base. Those are terminologies that'll be used when we get to chapter 10 as well. So what he's going to do, he's going to put this as the equation of line, which separates the fact that on this side it's nothing but air, and on this side it's the object. So then what he does is he said, hey, I want to go ahead and integrate across this. Now, I don't know, I think what I'm going to do, he does things a little weird here, but it turns out you don't have to do them weird. So what I'm going to do is I'm going to look and do this the way you would normally do in calculus. So let me do that right here. So we want to know, well, first of all, I'm not even sure I care too much about doing this. because I know this is just the base times the height and over 2. However, maybe it is a good exercise for us to do that. So if I do this and I look at a D area, let's say we're going to do this D area. I'm going to run it from left to right. So the question is, in a D area, do I do a dx dy or do I do a dy dx? And what are the implications of doing one versus the other? Okay, so what I'll do, I didn't put them too close, so I think I'm going to separate them, or maybe erase that one and look at this one first. So I'm going to say I'm going to run it along dx. Let me get rid of. So if I'm running it along dx first, I take my object, my little D area, and I'm running it from here all the way across to here. But if I move up to about right here and I'm sliding it across to here, I'm stopping it right out here at this. Let me see if I can do this. At this value of x. So what is that value of x? Or maybe I should do, okay, so here, let's look at it this way. If y, if this is true, then I can take y, multiply times b, divided by h, and that would be base minus height, base minus x. So I'm taking this equation and I'm reducing it. Then I'm going to move that across. X is equal to, move that across, be b minus y times b over h. I think I'm going to run out of space. I wonder if we can actually do this. I've never tried this. I'm going to do a copy and see if it can just paste it directly into one of these. Never tried this, so I don't know if this is going to work. It doesn't work. So you know what I'm going to try to do? I'll take a few extra minutes, and I'm going to run out of space over here. So I think I'm going to take this picture, and I'm going to try to take the picture over to the drawing and work it over on the other sheet. Okay, it's having trouble here. All right, one more line to erase. Okay. Now, okay. That will copy. Okay. Everything is really slow on this thing. It's not the fastest machine out there. Oh, that was copied across. That's okay. So we're basically going down and doing this. Okay, and we're deciding whether we want to run dx first or dy. So what I'm going to do is I'm going to run dx first. So what I'm doing is I'm taking my object and I'm going to run it inside here. I'm going to run it from left to right until I hit this object line right out here. So this is the equation of that line, right? So if I take y times b over h, that will equal to b minus x. So x will end up being b minus b over h y. Or I could redo this by saying x is equal to b 1 minus y over h. Let's see if that makes sense. So if I put y is equal to 0, this spot, I end up going to there, which will be b. If this is 0, I end up, going to b, which is what I would expect. If I'm at the top, then y is equal to h, and this term is equal to 0, and x is equal to 0. That makes sense. So if I'm halfway in between, how far do I go? If I'm halfway in between, I'm at y is equal to h over 2. And so y equal h over 2 would mean that this term right here would be 1/2. 1 minus 1/2 would put me halfway over. So I'm pretty comfortable that that's the value that should go right in here. So again, what I'm doing, let me try to see if I can make sense of this. Taking my little square, I'm fixing it at a value of y, and I'm running it from left to right till I fill that whole channel, so to speak. So now I realize I got to back up and put b 1 minus y over h, and I've got to integrate. And that's that. But the problem is there are two integrals here. So how far did I go? You know, where did dx go from and to? Okay. Now, the other way to look at this is there isn't anything. I went from here, and I went to b over 1 minus y over h. So there's a value of 1 right there that sits in here. And I run myself from here all the way across to here. This time, the dy, I have to do these sweeps all the way across to the top. So it goes 0 to h. So if I integrate that, I wonder if this thing can do integral. Let me try this. I've never tried this, so let me try this. I know the answer to it. The first answer is 0 to h b 1 minus y over h, and then dy, and then I integrate that, this term, and I should break it apart again. If I break it apart like that, I'll get hb for this term. Here, I'll do it this way. I'll get b times y minus b times y over 2 to h, evaluated from 0 to h. Put in 0 for this, you get nothing. You put in h minus, okay, then you got to do b 8 squared over 2h. This term gives away one of the h's. So you get bh minus bh over 2, and so you get bh over 2, which makes sense because that's the area of a triangle right there. The reason I wanted to do that, though, was I wanted to set this up so that now I'm going to basically try to find x bar or y bar. So if I want to look for x bar, this sounds weird. Okay, let me do this way. I'm going to do this integral again, but this time I'm going to swap this dy and dx. Now, if I'm swapping it, I'll tell you what I need to do. I need to move this over to the right because I'm going to reference. So this is one example. Now let me swap the integration and see what makes sense there. If I swap the integration, what do I get? Okay, I'll do this. Swapping the integration. I'm basically going to integrate, but this time instead of dx and dy, I'm going to move dy dx. So what am I doing there? I'm taking a little square. Okay. I'm taking my little square. Okay, there's my square. And what I'm doing is I'm first running it north-south. So as I run it north-south and I move it across here, I'm basically, the top of the integration ends up being limited by h b minus a x. So So here I'm just taking that equation straight and putting it in here. But the integration that occurs, I guess I should put a 1 there, although usually nobody puts anything there. What happens is after I go north-south, I've got to take that and go north-south, and I've got to go east-west. So I've got to go from 0 to b here. It's not a mowing machine. I don't know what that is. Okay, so what happens to me is I end up doing this integral first, and I just drop down. Because of that, I end up dropping down h b minus x dx. Then I can play that out, and basically, I don't know, here's what I'll do. Let me do it this way. I'm going to do it individually. So the first term would be h minus, because the b's will cancel each other out. And I'll say x h over b. And now I'm dxing that, so I get hx minus hx squared over 2b, evaluated from 0 to b. For the first term, I get hb minus h b squared over 2b, which that cancels that, and so I'll get hb over 2. So I get the same answer. It just so happens that on one of these, I swapped and did the sweeping of the dx one direction, and then I did the sweeping of the dx a different way here. Because of that, my limiting curve equation changed. Now, here's why I'm relating it this way. Because this is kind of what you did in calculus. You didn't really do things directly the way he's doing them. So what he's doing is he's putting this straight in, and he's immediately going to this, to this, or to this term. This is what we're working on right now. How did he just go from here directly to here? And that's why I add this description, because there are two ways you can do this. One, you sweep your dA. You got two choices in an area. You have a D area. You can sweep it this way first, and then sweep your lines like this. And if you're doing that, in the inside, it's a dx first, followed by a dy. The dx is limited by the equation that happened here. The dy means you got to go from here to here. However, if you sweep them the other way, in other words, you sweep them vertically, then you are sweeping your y first. And your first integral is limiting the equation here, and you're sweeping from 0 to b. So you're sweeping these vertical lines, these vertical sweeps all the way across the area, and you're sweeping vertically up and take these vertical lines and sweeping across. Now, why does that make a difference? Well, if you take a look at this, you have the dy first here, and you have the dx first here. Now, if I'm turning around and I want to know now, I got two choices now. He'll have somewhere where you're going to say this, and he's going to have somewhere else where you're going to say that. Okay, so this will be x bar is equal to this, and the other term is going to be y bar is equal to the integral of y dA over dA. Now, these two are the same. But whether you put the X in there or the Y, it makes it easier based upon which way you decide to sweep. So, for example, if I want to, and now I guess I better change my color or something. So now if I go in here and I want to put something in, I can put the Y in here. Okay, so before I had this, so what I'm going to do is I'm going to copy this down. Let's see, which one does he find first? He found Y bar. Does he find X bar? He does not find X bar. So let's find both of them. So he finds Y bar first. Okay, where's my thing? Okay. So let's do the Y bar. So I'm going to go in here. And then after that, I'm going to do the X bar. I'm going here. Give me a second. I'm going to try to copy this whole thing. Circling all of this. Do a copy. Drop it right there. This time I'm going to start changing things around. What I'm going to do. Okay. I was about to say, I might have goofed this up, but I don't think I did. What I could do here. Yeah, I'll do that. Not sure that's really. So there I'm going to put a Y in. So when I integrate that, that's going to end up not looking like this anymore. It's going to end up looking like this, evaluated from H, hang on, B minus X. So, you know what I might do? I might save myself. Let's see. Okay. There it is. Takes it a while for me to. Okay, so this might take a minute to come up. Okay, so I know you can do this kind of stuff online, but a lot of those online things have this particular code as an engine behind it. So what I'm going to do, go into calculus, I'm going to do an integration. I'm going to integrate the expression, which is going to be, and the integration is going to be y. Okay, did it hit it? Okay. The variable of integration is going to be y. I'm going to make it a definite interval. I'm going to go from 0 to, now I've got to be able to go in here, h over b minus x. It's going to be weird. H divided by b times b minus x. Oh, I got an extra term there. I'm going to do this integral. Uh-oh. Do I have a... Did I not put a... Okay, let me try it again. Oh, that's supposed to be on the outside of that. There. Did I get an extra term? Okay. So I get this. Okay, this looks awful. But then, okay, why did I do? Okay. Okay. Let me go back and see if I can fix this thing. Okay, let's see. It does an integral inside of an integral. That's not exactly what I want to do. Integrate y. Everything got goofed up there. Yeah. Integrating y from y. Integration from 0 to now. Okay. Can I move it to the side? Yes. H divided by b times parentheses b minus x. Have an extra. Then I'll go through and do that. Okay, now I'm going to go in here, get rid of this term. Why didn't I get rid of it? Okay, so there's the first integral. Okay, so what I've got to be able to do is now, okay, so if I were to copy this down, I mean, I could, but it's kind of a pain to do so. So now that I have this, so that's what this term right here ends up looking like up here. So this is telling me now I've got to integrate that term, dx, from 0 to b. So let's see about doing that. Now it turns out that in this thing, you can do something interesting. You can, the parentheses, or I mean the percent sign means take the last output and integrate it. I'm going to integrate from 0 to b. And I get that. So it turns out that b times h squared over 6. Now if you look back at the book, you'll see that sitting right there. Now, so again, what we've done, okay, so what this does right here, let me see if I can take a snippet of this, and then I'll tell you about what this code is. So what we've actually done, I've tried to make things easy for myself by just going and doing this. So the first thing I did is I integrated inside the integral was y. So here, I'll do it this way. So inside the integral is the y. I'm integrating with respect to y. My limits are from 0 to h over b, b minus x. And it gives me that. So then the next thing I do is I take this equation and stick it in here in the parentheses, and I'm integrating with respect to x. See, there's a bunch of x's in here. And then I go from 0 to b, which is what I'm doing next. And I get this value, which is the same thing that he got. So if you look back at the equation looked like this. Y, b area, over integral of d area is equal to y bar. So in the upper part, I got bh squared over 6, and the bottom, the area, is bh over 2. That's bh over 2. So it ends up being h over 3, which is what he ends up with there. Now, let's try this another bizarre way. And this is where, if you're in calculus, so you can do this one way or the other. It's kind of up to you. You should get the same answer. So let's do this the other way, so that what I'm going to do, I'm going to, give me a second, I'm going to copy this thing. Okay, so really I should delete all this. Then we'll go across over here. We'll drop it down. This time, I'll try to do this. I'll try to go in here and put in the y right here. And so, if you put in the y right there, what do you get? Should you get the same thing? I don't know. You might supposed to. So let's see if I can hammer this one out. And I'm making it available so I can see the whole thing. So now I'm going to start the integration over again. But this time, oh no, that's in the way. Okay. I'm integrating. The term I'm integrating on the inside is a y. I'm integrating with respect to x, but I'm doing a definite interval, and I'm going from 0 to that upper term, which is b times 1 minus y divided by h. And it put another percent sign. Okay. So I do that, and I get that. Now the next thing I want to do is integrate that, the percent sign, with respect to y. And I'm going to do a definite interval from 0 to h. And it jumped on the screen, but what you should find is, in fact, it's the same thing. So it does not matter whether you sweep your things vertically or horizontally. It does not matter. You still will get the same answer. What you notice is this. In deciding which way you're going to sweep, sometimes you can end up with a very complicated equation like that one, or you can end up with a simple equation like this one that sits right here. Sometimes you won't know. Sometimes you will. It just kind of depends. So, in fact, what he will do throughout this book, and this is something that you're going to see that might be annoying, is he takes a vertical bar and looks at the deep or horizontal bar. Here he takes a horizontal bar. He looks at it. Okay, let's let it kind of come up. It's got to come into focus eventually. Okay, so he looks at this vertical or horizontal bar, and he works off of that. That's not what you're used to doing in calculus. What you're used to doing is if you have an area, you're used to doing, okay, you're used to doing this. That's what you're used to doing. And in my mind, that's what you should stay being used to do. So to me, the way he does these, I don't like, because it doesn't build off of what you were doing in calculus. So let me give you a background of what this code is and where it came from. Gosh, this thing is so slow. Okay. Yeah. If you go out there and search this, you're going to find a couple of things. First of all, you're going to find a car. But then, not too far under that, you're going to see a computer algebra system. Sometimes that might end up on top. Sometimes that might end up below. I think I touched it. Okay. So this is one of the first early renditions of all these computer algebra systems that exist today back in the 60s. Now, what's interesting about this, now maybe they're able to do this better now, but back, I was working back in around the 2000 range, and I had at my disposal 4 or 5 different computer algebra systems to find the eigenvalues of a symbolic 6x6 for wave propagation. This was the only code that solved it. All the rest of them wouldn't solve it. So I sort of stuck to this one because I haven't seen, because I was using Maple Mathematica. They were not able to solve it, but this one was. So I've basically stuck to this thing. The thing is it's free. You can just go to downloads. And the graphical user interface, which was put in later, actually kind of guides you through it. You can just go to the installation for Windows or Mac, and the reason this is slow is my computer. It doesn't have anything to do with this. And you just go in and download it and install it. The nice feature about it to me is you've got all these that are sitting there. They kind of guide you through it. What you find out is you go through and integrate. It gives you this little pop-up. It takes you through it, but then as a result, it drops that on the page. Then what you find out, you could say, well, you know what? Maybe I was supposed to put an x squared there. So you put an x squared, you hold the shift down and hit enter, and it integrates it again. And so then you can say, oh, you can go back. You can actually write a program in here to change things around and have things happen pretty nicely. In any case, that's essentially what I'll use to kind of take us through it. I know there are other online systems that do this as well, but I'm just going to stick to this. So the only thing I think to get out of this is how you sweep. In other words, if you had a function, this will work on any function. If you had a function that you're integrating something across, and say you had something like that, and you're integrating from, say, 0 to 10, and this is your f of x, so y is equal to that. You're deciding whether you're going to sweep across here, and then sweep up, or sweep up and then across here. So it's basically whether your integration is going to take place like this, and going from one end to the other, or your integration is going to take place like this, and you're going to go that way. So that's the only thing, and that's basically which one comes first, dx dy or dy dx. And then you have to look at what the limits are. What are your limits going to be as a result of that? So what we'll do is, I don't know what's going on with my watch and my phone, much less the computer, but we'll do several objects like this. The end result of this thing is this. The centroid of a triangle sits 1/3 base over 3 here, and it sits height over 3 here. And that's where the centroid of a triangle always sits. Square is pretty obvious. The centroid sits right in the middle, so it'd be base over 2, height over 2. So we'll do some of these other weird objects he's got. Here's got some circle, half circle or something. Some function, some weird function there. What we'll do next time is we'll do all 4 of these. These might be some of the ones I actually put on the homework. So we'll do some of these. We'll look at how you can move across the, maybe I'll do 1 or 2 of these too, because these are odd enough functions that they should be interesting. Maybe this one too. That one might be a good one to do, because that one would be interesting, because if you're sweeping from left to right, you're hitting the bottom of the function to the top, and then you're going from 0 to 2. If you're doing vertical, you're basically going, okay, if you're doing vertical, you're going from the function to the value of 2, and you're sweeping across from -1 to +1. And so the key is to identify where you're sweeping, what you're limiting your sweeping, and what is your boundaries on your sweep. And so we'll do a bunch of these till we figure it out, because everything we do here, believe it or not, all we do in the next whole chapter is right now we're putting a value of 1 or a value of x or y in here. Guess what? In the next section, chapter 10, we put an x squared or a y squared in there. And that's it. So if we get used to doing these integrals to cover all these, all we're doing is adding a square term, and we're making a new chapter out of it. And that's it. There is some weird implications about that x squared and y squared that we'll cover called parallel axis theorem. And I'll show you how you can go about doing those. And then we'll be done. That'll be it. So actually I may have spoke out of turn. I said we do 2 days and then 2 days. I think we'll end up doing 2 days and then 3 days. So do 2 days on centroid, 3 days on the second momentary. And then we're done. So, and then we'll still go back, but I'm hoping that questions get generated. And I think we still got 3 weeks. So we'll be done a couple of days, maybe a week early. So any questions? Anybody have any questions or anything? If not, I guess, what time is it? Well, it's almost time to go.